we are going to apply a thermal load to a bonded material beam with copper on the top layer and aluminium on the bottom layer. As the temperature increases, the two materials will expand differently with different amounts because they have different thermal expansion coefficients. Since they are bonded together, this generates internal stresses and causes the beam to bend. Now observe the deformation and the direction of the curvature, bending curvature. So if you go to applications here and you go to simulate, you can see under refine model, review geometry, apply, that they are bonded. This is a default setting when you assemble the two parts. And by the way, you can on the view, when you assemble them, you can make them different colors here by, as you can see, you have aluminium here, the color for aluminium and the color for copper. Yeah. So when you are in the simulation, you can apply a boundary condition here, or constraint, whatever you want to call it, displacement, and you lock the translational directions, and you apply a thermal load here, temperature, and you go uniform components. You choose both of the components, copper, aluminum, and you want 200 degrees Celsius, and the reference temperature, that is the room temperature when you glue them together. So we have boundary condition, thermal load. Now we just create a new study, temperature, and everything is default, single pass it active, and you run this. Oh, we forgot to apply a material to the parts. You apply a material assignment, go to this, and you go to non-ferrous metals, and you choose rough aluminium and copper rough. Okay, so you choose the upper part, copper, and you apply copper to it, and you assign aluminium to the bottom layer. Now you can run the study. Let's deform it, and don't animate it. As you can see, it bends upwards because aluminium has a more thermal expansion coefficient. It wants to expand more, and you have more stresses here, even though they are one misses. Let us check the Z direction. Instead of fixing the part, you can apply soft springs to some points, and you can see how the stresses look for that. And by the way, let me just show you what I mean by CTE, coefficient of thermal expansion. This is for aluminium 23 times 10 to the power minus 6, and copper has a little bit less, so it doesn't expand as much when you apply a thermal load to it. So let me just change the constraint. You delete this constraint here. You can right click on the constraint and delete it. And now we can apply, we go to springs here, you choose to ground, and you choose 4 points just to prevent when you apply a load, to prevent the part to move when you apply the load. Rigid body motion when you apply a load. So you have the points, you create springs with some stiffness in the to the extensional stiffness and torsional stiffness. You just apply some stiffness values. This is the units, and you just apply it, and now you can run the analysis. You can create another one just to see. Single facet active and everything is default. Now when you look at the results here, you can see there is no constraint here. So this is one misses stresses, and when you look at the Z direction, this is the shear stresses when you apply the thermal load. This bonded interface introduces some shear stresses between the copper and aluminium part. For our case, 20 to 200 degrees. When you apply this thermal load, you get that much stresses between the parts. And you can investigate the part more closely. You can see the stresses. So this is how you apply a thermal load to a bonded material beam, and look at the results, the deflection, how it expands. So yeah, don't forget to like and subscribe if you enjoyed this video and learned something. Thank you.